gas. We don't see it, but trust me, it's all around us. Remember when you popped your first can of soda or when you first watched a hot air balloon festival? Gas was there. Try to recall your childhood. I personally was not a child back then. I would run around until my mom bribed me with food just so I would sit still. In a way, gases are like that too. They don't behave or just stay in one particular area. That's why scientists and mathematicians alike found it hard to describe them theoretically. The first gas that was described mathematically was Boyle's law. Its proponent is Robert Boyle, a rich Englishman who had a lot of ideas on chemistry and science. The Boyle's law states that the pressure and volume of gases are inversely proportional with each other, so when the pressure goes up, the volume goes down, and vice versa. Simply put, it can be expressed in the equation P1 times V1 equals P2 times V2. Boyle's law assumed there's gas present, and that gas goes through changes. P1 times V1 is the pressure and volume before the change, multiplied together, equals P2 or V2 or the pressure and volume after the change multiplied together. This can be applied in the respiration cycle, so when we inhale and exhale, our diaphragm contracts and expands due to the change in pressure, which in turn affects the volume. Let's have a sample problem for us to understand this lesson better. At 1.7 atmospheric pressure, a sample of gas takes up 4.25 liters. If the pressure on the gas is increased to 2.40 atmospheric pressure, what will the new volume be? So as we said before, there's a change that takes place. We have the before pressure, which is 1.70 atmospheric pressure, and the before volume, which is 4.25 liters. Then, we have the second pressure after the change, which is 2.40 atmospheric pressure. We don't have the volume, so it's going to be V2 that we're going to be solving for. We want to rearrange this and move P2 under P1 times V1, so it's going to be P1 times V2 divided by P2 equals V2. Plug in our numbers and do the math. First, 1.70 atmospheric pressure times 4.25 liters divided by 2.40 atmospheric pressure equals 3.01 liters. Therefore, our V2, or the after volume, is 3.01 liters. Up next, we have Charles' law. You might be wondering, what exactly is Charles' law? Well, this is named after its proponent, French physicist Jacques Charles. He suggested that the volume of a gas is directly proportional to the temperature. So when the volume increases, the temperature also increases. This relationship can be determined with the equation V1 divided by T1 equals V2 divided by T2. Cross-multiply this and we get V1 times T2 equals V2 times T1, where V is the volume and T is the temperature. You can see this in action if you, for example, heat food in a microwave inside of a sealed bag. One thing you might see is that as you open the microwave, the bag is much bigger than it was before. Now, let's have some sample problems in order for us to understand this gas law better. First problem. A gas occupies 900 milliliters at the temperature of 27 degrees Celsius. What is the volume if the temperature is changed to 132 degrees Celsius? So, you are given 900 milliliters as your initial volume, which is your V1, and 27 degrees Celsius as your initial temperature, which is your T1, and 132 degrees Celsius as your final temperature, which is your T2. What we are missing is our final volume, which is the V2. First of all, we have to convert our temperature from Celsius to Kelvin. It's very simple. All you need to do is add 273 Kelvin to your given Celsius. So, 27.0 degrees Celsius plus 273 gives you 300 Kelvin, and 132 degrees Celsius plus 273 gives you 405 Kelvin. Now that we have converted our temperature to Kelvin, we then switch the variables in the equation. V1 times T2 equals V2 times T1. 900.0 milliliters times 405 Kelvin equals 300 Kelvin times 900 milliliters times 400 Kelvin equals V2. 300 Kelvin, and then now we get the V2, which is 1215 milliliters after completing the equation. Lastly, we have Gay-Lussac's law. Its proponent, Joseph Gay-Lussac, is a French chemist, and the law is patterned after his name. Gay-Lussac's law states that at a constant volume, when the temperature is high, then the pressure is also high. They have a directly proportional relationship with each other, so when the temperature goes down, the pressure also decreases. To express this in an equational manner, take P1 and divide it by T2 equals P2 divided by T1. Cross-multiply again to solve for the values. Here's a sample problem. If a container of oxygen exerts 1 atmospheric pressure at 25 degrees Celsius, what temperature, in Kelvin, is needed to change its pressure to 2 atmospheric pressure? So, you see that you're given 1 atmospheric pressure as your P1, 25 degrees Celsius as your T1, and 2 atmospheric pressure as your P2. We need to find our T2. Let's start. So, first thing you need to do is to convert your temperature from Celsius to Kelvin. To do that, you simply add 273 to your given Celsius. So, you do 25 degrees Celsius plus 273, which gives you 298 Kelvin. Next, substitute the variables to the equation, then do the math. P1 times T2 equals P2 times T1, then substitute. 1 atmospheric pressure times your missing T2 equals 2 atmospheric pressure times 298 Kelvin. Now, to solve for the T2, 2 atmospheric pressure times 298 Kelvin gives us 596 Kelvin. That is now our T2. Hooray! We now have 596 Kelvin as our final answer. Kind of heavy to digest, isn't it? So, consider this. Take this for instance. Imagine preparing a small basin filled with water with lots and lots of ice. Then let it go for a few minutes. While that's being done, you go heat a soda can that's half filled with water and set it to boil. When you already feel like, is it just me or is it getting hot in here? Well, actually, it's time for science. Go place the heated soda can immediately to the basin, then boom! Did you see that? Science is fun! But how did this even happen? When the temperature is high, the pressure is high as well. Otherwise, when the pressure is low, then the temperature is low as well. The basin with iced water was less since the temperature was low. With this being said, the sudden change of pressure caused the soda can to crush. Hope this helped. Remember, science isn't just about the technical stuff. You have to learn to apply it in your everyday life and immerse yourself in it. Now, this has been Michel Urbano claiming na kapit lang gagraduate tayo, and that's a wrap.